In this video, we begin a new unit, Unit 13, devoted to the electric current and direct current circuits. In this unit, we will still work with charges, and there will be electric fields and potential drops, and we're going to work inside conductors. But there's a big difference from the last unit, and it is that in the last unit we were mainly working in the electrostatic equilibrium when we were talking about conductors. This is conductors in which the electric field was zero inside, and they had the same potential, and charges were not moving. Now in this unit, charges are going to be moving because there's going to be a potential drop inside the conductor, and there's going to be an electric field pushing the charges to move. And this is going to be caused by some energy put into the system. So in the first part, which we're going to tackle in this video, we're going to talk about the electric current and the motion of charges. And then we will continue to introduce new concepts as the resistance, which is going to be the resistance that any conductor is going to put against the movement of charges, because the movement of charges is going to cost some energy, and the conductors are going to put some resistance. Then we will look at the different energetic terms for these movements, and in point 4 we will tackle the electromotive force. Which is not really a force. You have to be careful here with the terms, because the electromotive force is going to be really an amount of energy per unit of charge that we're going to have to put into the system for the charges to move. And at the last part of the unit, we're going to talk about direct current circuits, which are circuits, very simple ones. We're going to have batteries and resistance mainly connected in series and in parallel. We're going to play with them a bit in this fifth section of the unit. So we begin by talking about the electric current, which is a measure really of the motion of charges inside a conductor. We will begin by defining it, and then we will define a very similar concept, which is the current density. So the definition of the electric current is as follows. It's the rate of flow of charges through a surface. This is how many charges are crossing a surface per unit of time. This, in mathematical formulation, would be given by the amount of charge, delta Q, divided by the amount of time that this delta Q takes to cross a certain surface, which is delta T. So the electric current is given by I. We're going to denote the electric current is going to be given by I. In the limit, when the time is very small, the electric current is the derivative of the charge that crosses a surface. Remember that we always have to cross the surface in time. Okay. So in the international system, the unit is the ampere. And this comes from the proposal of this physicist in the 19th century, who was the first one to talk about the electric current as a flow of charges. So the relationship between the unit, the ampere, and other units is that the ampere is 1 coulomb divided by 1 second, which is very easily to follow from this equation here. So let's the electric current is a macroscopic quantity. It's something that we can measure macroscopically. However, this is really related with microscopic things that work at very, very small scale. So to bridge the gap between both, we're going to introduce a concept that is called the drift speed. So the drift speed given by Vd is going to be the average speed of the mobile charges when we put an electric field. So whenever we think of a piece of wire, where we have a potential drop. So we have installed an electric field. This electric field is going to provide a force that is going to move each charge. This force is going to be big because remember that the mass of the mobile charges usually is very low, because normally the mobile charge is going to be the electrons, and these have very little mass. So the force is big, so there's going to be a lot of acceleration, and they're going to move quickly. However, they're going to move in their speed of each mobile charges is going to be different because they're going to interact with the ions of the conductor, and but we can always think of the average speed of their movement, and this average speed is the drift speed. Okay, so think of a conductor. Here we have a wire, okay, and we, as I was saying, we want to relate the macroscopic, which is the electric current, with things that happen microscopically. This is the small mobile charges. So in this wire we have a number of mobile charges per unit of volume, which we call the number density, and we denote by N. And each we're going to simplify the picture. We're going to think that we only have one type of mobile charges, and they all of them have the same charge, which is Q. So each mobile charge has a charge of Q, and then we're going to call A to the area, the cross-sectional area that they are crossing. Okay, so I'm going to do another drawing here. This is the same idea. This is the area A. And I'm going to try to relate the intensity, the electric current I, which is macroscopic, with these more microscopic quantities. Okay, so this is the area. This is that the charges are going to cross, and this is these are different charges that I have in that piece of wire, and each of them I'm thinking that they are all moving at the same speed, though we know it's not true, but in average term we can work with it as if it were true. So each of them moves with the drift speed. Okay, so imagine we have delta t, we pass some time, which is delta t. So the amount of the length that each of these mobile charges can move is going to be given by L equal Vd delta t. Okay, this is just a length. So imagine this is the length, this is L. Okay, so during delta t, this mobile charge is going to be able to cross it, and this one also is going to cross. So we can really know how many charge is going to cross, because if this is L, this amount of length is L, then all the charges that at certain moment are inside this volume are all going to cross this area in the time delta t. Okay, so we know that the number of charges that are crossing is going to be given by N, which is the number density, how many per volume we have, times the volume of this volume I've plotted here, which has an area of A, and it's a cylinder, and it has a height of L, which was given by Vd delta t. Okay, as each of these charges, this is the total amount of charges that can cross A in delta t. So if we multiply by the charge that each mobile charge is carrying, there we have the total charge that is crossing this area A in that time. So the intensity is going to be delta Q divided by delta T, which is directly the charge of each mobile charge times the number density times the drift speed times A. The area. Okay, so this is what is written just here, which I just explained. Okay, So we are, as I was saying before, we relating the macroscopic measurement of the electric current with some microscopic measurements, which are the mobile, how many mobile charges I have per unit volume, what is their drift speed, and how much charge we have for each. Okay. There's one thing here that we are always thinking of segments of wire, okay, and we could expand this idea of the current of the electric current to something that doesn't need to be in a wire, and that is for that we're going to use the current density. Okay, so the current density is going to be a vector given by the amount of charge each mobile charge has, times the number density, times the drift speed, but this time the drift speed it's also a vector. Here in the previous definition, it was used more as a scalar because we already knew what the direction of the current was. Okay, so we can relate this amount, which is a scalar, the current, the electric current is a scalar, with this other amount, which is a vector, which is the current density, because between both the only difference is the area. Okay, so to make it very general, we could have this idea that the current density could be very different. So we can plot it as lines here. So this line here is showing the current density, and this other in other parts. And then if we want to know the total electric current across a surface given by this surface, this green surface, what we would have to do is just make this integral. Okay. So if things are if we simplify things and say that S is just this area A and that the current density is uniform, then in this simple case of the wire, again we would have that I is equal to J times A. Okay. But in more general terms, we can just use this expression, which is using the integral.